Hello, I'd like to welcome you today to the CMI webinar series designed for and by CMI. And I'd like to, again, not only welcome you, but our series, our webinar is on cerium gap magnets today. And I'm going to tell you a little bit about the logistics of the webinar here. First off, we are broadcasting from Colorado School of Mines, hosted by, but of course, we're everywhere across the nation. If you have a suggestion for a future webinar, we'd love to hear, because again, we are designing these for you, for our body of the Critical Materials Innovation Hub. This is a public webinar, and the recording is going to be available at ameslab.gov/CMI. And it is under the webinar menu and on YouTube, also which is on the Critical Materials Innovation Hub channel. Questions? We know you'll have some. It's going to be a great presentation. So please, as soon as you have a question, would you go ahead and type it into the Q&A section? That way it'll be queued up and we'll be ready when we are taking questions. I am your moderator today, so I'm going to be working through this, trying to keep everything going, and I'll come back on again for question and answer. But I'd like to introduce our presenter today is Dr. Andriy Palasyuk, and he's a scientist too at Ames National Laboratory. He has his PhD from Ivan Franko National University of Lviv, and he has several expertise areas in the materials discovery, development of novel, cost-effective alloying approaches, and more. He's been a part of the Critical Materials Innovation Hub since 2016. And he's also recognized by the U.S. Department of Energy Technology Commercialization Fund, and has led successful industrial collaboration on scaling and test manufacturing of CMI's technology. You're going to learn more about that. Andriy, I don't want to take any more of your time. Please take it from here.
Thank you, Cynthia, for your very comprehensive and kind introduction. So, hello, everybody. My name is Andriy Palasyuk. I hope everybody hears me well. So I would like to start this webinar and talk about our technology and talk about how our technology, what the technology is and how it develops. And recently we have received recognition of our technology. We are recognized as one of the best 2023 R&D technologies in the world. And just to give you, some highlights of what it is and how is it useful. So we call it cerium gap magnets, or CGMs. This is developed in Critical Material Innovation Hub. And here is our outline. So I would like to talk a little bit about global magnet markets and processes. And I would like to touch the base what the gap is in the magnets, for example, between the magnets, if you wish. So then I would like to talk about what is some prospects of rare earths and why is this so. Then about the system which we started to develop, about the single crystals, and about stacking faults. Then we compare our system with other magnets, especially with Alnico. So about temperature performance of our system, about scale-up possibilities and actually results. And then about perspectives, if you wish, or future perspectives, conclusions, and then, thank you very much. So when we look on the present global markets of permanent magnets, and when we look on the processes, how those permanent magnets are produced or manufactured, we see these two basically lines. The upper larger circle diagrams and lower, smaller circle diagrams. And the larger circle diagrams actually represent what kind of players we have on the market. And as you see, we have not many players, basically only 6 of them, and only 4 major players, 1 player which is mixed with polymers, for example, neodymium iron boride bonded magnets. And then we have just a little bit of other participants. But for some reason, it is very profitable to have on the market only 2 players, neodymium iron borides and ferrites. For example, production-wise, ferrites are occupying almost 82% of the market. But value-wise, neodymium iron boride is a champion. So why is it so? We can talk about performance and we can talk about price. So, but when we talk about performance, neodymium iron boride is much significantly better than ferrites. And but nevertheless, ferrite is also very much dominant on the market. So then when we talk about price, we see that ferrite is absolutely dominant on the market. So it's not about price, it's not about performance, it's about price/performance. This is what is important. And price performance is actually very favorable for those 2 candidates. But for some reasons, it is absolutely not favorable for other 2 or 3, permanent magnets on the market. What is also interesting is how those players are manufactured. And if you see, only one of them is manufactured in more or less, how to say, simple way. And this is Alnico, because it's cast. Others are sintered. So, but it doesn't help Alnico to be a major player, because price performance of Alnico is not fulfilled. So this actually comes to the point that it is very important to know how material costs, how critical the materials are in the permanent magnet, how much the process costs, and how an uninterruptible process is. It all actually summarizes onto dollars per megagauss/stat. And there is an assessment of John Ormer, which which is depicted here on the upper part of this slide, and which actually shows the diagonal line, the line of dollars per performance. And this line, in fact, separates niche market and mass market. And surprisingly, but maybe not surprisingly, ferrites and neodymium iron borides are only players which are satisfying mass market requirements. So you have to be in the price range of $2 per kilogram per megagauss/stat to fit or to be accepted in the mass market. But there is a disconnect, and this disconnect is that on this line we see very opposite points. So in the very low performance range, so basically having very bad performance for very low price, or we have basically very nice performance for very high price. And this is a limitation because there are many applications where we don't need very nice performance for very nice price. And we cannot fit that performance into many sizable application or size restricting applications. So that's why it would be nice to find a player or a permanent magnet which would satisfy the middle of this red line. So to say, we need a middle performance for the middle price. For example, we need 20 megagauss Ørsted performance for $2 per kilogram per megagauss Ørsted. We need less expensive material. We need less expensive process. And in fact, it would be okay if we had a hard ferromagnet with magnetization, hard ferromagnet, so basically with enough magnetic crystalline anisotropy, with magnetization, which is between 5 and 12 kilogauss, closer to 12 kilogauss than to 5. And why do we need that? We need this because electrification is coming up, applications are coming up, a lot of possibilities for electrifications are coming up, but supplies are coming down. And in fact, from these diagrams depicted on this slide, we see that by 2030, for example, supply will be absolutely critical, supply of neodymium. And neodymium is basically the main element needed for perfect magnets, for neodymium iron borates. Neodymium, but also dysprosium. So by 2030, allegedly, seems like we will be out of neodymium dysprosium. But the market and the applications will grow, electrification will grow. So we would need something that will substitute them. What can substitute them? And when we look on the rare earths, cerium, lanthanum, they are in great abundance. There is no problem with that. So simply wise, or in a very naive way, it would be good to substitute neodymium or dysprosium for cerium and have another possibility. So this is my thinking basically some years ago. Yeah, cerium looks to be excellent substitution possibility because it's abundant, domestic, and cheap. Except when I learned then later, cerium is very poor substitution possibility because cerium brings mixed valency, and in fact, in permanent magnets, this mixed valency thing actually spoils everything, and it is very difficult to make good permanent magnet out of cerium. But nevertheless, we took this cerium cobalt 5 hard magnetic material and tried to work with that. Cerium cobalt 5 is very isostructural with samarium cobalt 5. And everybody knows that samarium cobalt 5 is a maximum magnetocrystalline, has a maximum magnetocrystalline anisotropy. So it's very, very hard magnetically. And it's also because, in part, it is because of the crystal structure. This crystal structure is unique. It's a layered crystal structure with interesting 1D dimensional channels where you have nominally cationic big atoms, large atoms, and smaller atoms, transition metal atoms. They are spread throughout the network, anionic, nominally anionic. And this is very interesting feature of this crystal structure because there is a possibility for magnetization boost in this crystal structure. Sometimes in those one-dimensional channels, there is a possibility to introduce transition metals. So basically, you can shift your composition and increase the magnetization. So this is kind of flexible crystal structure. Yeah, we worked with Cerium Cobalt 5, but Cerium Cobalt 5 is absolutely horrible from the perspective of practicality until you put a little bit of copper in it. And when you put copper in it, you will see that everything magnetically changes very much because extrinsic magnetic properties develop even in nominal single crystals. For example, here we grew single crystals and we heat treated them. Those single crystals transformed themselves easily into the permanent magnets with perfectly square hysteresis loops. And for example, in the central figure, you see 10 milligrams of single crystal plate is holding 1 gram of the weight. So it's very interesting phenomenon where you have extrinsic characteristic appear readily after the heat treatment. And we developed it, in fact, and we reached in single crystals, in nominal single crystals, if you wish, because you will see later that these are kind of not single crystal anymore. So we reached 10 to 11 megagauss stat. We kind of dissolved or diluted cobalt already with some other elements, and price to performance of this material starts to be attractive. So we were wondering what is the structure of single crystals, and at the beginning, when we did our synthesis in the tantalum crucibles, we found precipitates after the heat treatment. But those precipitates, they were tantalum rich, but they were not related to the coercivity. They were basically camouflaging the real structural defects. So then we avoided tantalum. We did it in very practical alumina crucibles on a small scale, and we added iron to further decrease cobalt concentration, for example, in the original Cerium Cobalt 5 system. And when we did it, we found that system is still very, very magnetic, very square hysteresis loops, but it was very difficult to understand what are the defects, what is causing those square hysteresis loops. Even from the conventional X-ray and SEM, it was very difficult to see what is going on inside. Until we did more deeper TEM analysis, and we found that the matrix of the material is decomposed during the heat treatment because of the reduced solubility of the matrix at lower temperatures. And then the reduced solubility brought appearance of stacking faults, basically stacking faults and or inclusions or intercalated regions of secondary phase. This secondary phase was distributed uniformly, but not regularly. And obviously, this secondary phase was corresponding or responsible for appearance of coercivity. So when we compared it to the similar structures, we saw that this is not very unusual. There are many cases where you have combination of the matrix and stacking faults. Those stacking faults basically are inclusions of 1,2 type fragments into the matrix. But as I said, in our case, it's irregular but uniform distribution of those stacking faults. So then, basically, this gave me an analogy to what I did before, because I was working on Alnico. Alnico is a system where you also develop some kind of intragranular microstructure. And in our system, in this CGM system, we also develop intragranular microstructure. Coercivity is appearing not because of the grain development and sintering. Coercivity is appearing because of something that happens within the grain. For example, in alnico, we have spinodal decomposition, which is happening within each grain of the material. And here we have another kind of decomposition, but it is also happening within each large grain of the material. This simply means that this system can be or has to be processed like alnico. And maybe you remember at the very beginning, I said the casting is more profitable or easier than the sintering. Why? Because casting doesn't have many processing steps. So it is interesting all of a sudden. And what is even more interesting that the temperature characteristics of these metals, of this system, is also kind of similar to alnico. So for example, you see that alnico is almost a horizontal line at the bottom of the left chart. And our system is not that horizontal, but still, you know, very, very stable. So we decided to try to scale up the system, and we decided to try to cast it. And this was done within the TCF project, where we worked together with Bunting Du Bois. We were doing the casting part of this, and Bunting Du Bois was trying to make a bonded magnet out of the powder, which was received from casts. And it was successful. Casting was successful. I will just touch the casting part of this project. In fact, we were able to reproduce the material which showed practically reference characteristics, lab reference characteristics, and we were able to use commercial cerium for our experiments. So this is, for example, scaled up to kilogram scale material. In fact, we were able to optimize the process to one step, which includes synthesis. And because of the slow and controlled cooling, it is all combined in one how to say, in one pot, one step process. And your magnetic properties are actually developing during this melting and slow cooling. You see, this is the slide which shows the ingot consistency. We took different parts from the ingot and measured those, measured the hysteresis loop, demagnetization curves, and the coercivity is fluctuating within 5%. Magnetization is even less. So this is, to our mind, I mean, for our opinion, this is quite consistent. So this material has a potential, and if the microstructure is developed perfectly, and if this boost, which I mentioned in the crystal structure, is realized, then this system can be basically 20 megagauss-Ørsted system. And in fact, this also is realized when cobalt is reduced by another 5%. So in fact, we are reaching alnico level cobalts, but 20 megagauss-Ørsted performance. And we are coming to the point where we will compare price to performance. And comparing price to performance, we can look on our system from two perspectives, from alnico perspective and from samarium cobalt perspective. From alnico perspective, we have system which costs practically like alnico because process and cobalt level which is the priciest part of alnico, is almost the same, but performance is 3 times larger. So basically, we are shifting alnico to the right, if you wish. And from the Cerium cobalt perspective, we have a weaker system, but which is made much more simpler than the conventional Cerium cobalt. So basically, we are moving to the down because we are reducing the costs of Cerium cobalt. And in fact, we are in the process of penetrating this diagonal line between niche market and mass market somewhere in the vicinity of 20 megagauss or step. So we are creating another mass market permanent magnet for middle performance applications. So this idea and this realization was recognized by R&D 100. And this is basically our technology. I wanted to thank all the people which helped us develop this. Especially, I wanted to thank Tom Lagrasso, Helena Hasdosian. She was the program manager of the Technology Commercialization Fund project. And I wanted to thank you very much for your attention. If you have questions, I would like to answer.
Andriy, I want to thank you so much for a great presentation on your R&D 100 award-winning research. So that Cerium gap magnets. It was interesting to have you walk us all the way through and talk about cost as well as process, and that you have with your gap magnets potentially started opening up a middle market for gap magnets, and that's what is making this so successful. We know we have an abundance of cerium, and it is more cost effective, so very good on the research, and I'm sure that's going to continue on as markets open up. We do have a question ready, and it's from David Reed. If you want to read that and answer it.
Yes, I will read this. Is the development of gap magnets very much an interactive process, or can modeling be iterative process, or can modeling be used? And if so, how accurate is it? And the second one is, where in the middle do you think is the best? Because this is a very large gap. Or how did you decide where to target filling the gap? I would start to answer the second one, because where you are on that line is very much dependent on the performance. I mean the base performance of the system. So you can choose to be on the top of that diagonal line, but if your system is not performing like 30 megagauss or stat, then there is nothing to do. I mean, it has to be performing first magnetically, and then you have to figure out how to make this material as cheap as possible. So for example, for us, this middle ground is lower. It's closer to ferrites than to neodymium iron borates. But the way of making it is allowing us to talk about price performance acceptable for the mass market. So then, is the development of gap magnet very much iterative process? I think modeling can be used, especially to model different possibilities of the microstructure and how they are related to the development of the coercivity, and also how the grain structure is influencing on the coursivity. I hope I answered your question.
We do have time for additional questions. So while we are waiting for those additional questions, Andriy, is there anything else that you wanted to add of, where you're going, or again, the success that you've had and how it allowed you to have a successful R&D 100 application as well?
So we are going into the industrial realization of this concept, and we are going to optimize the process and see if it is possible to test these materials in the real application, for example. And we are going to organize the team which will be doing that. In fact, recently we were able to prove that this is the castable material. So because before we were casting, but casting was not really full, I would say, complete. So we were basically baking our magnet, if you wish. But now we are closer to the point that we can say that it's really castable system. Yeah, that's what I wanted to say.
Also, Andriy, how was your process for that you went through as you were writing for your application for the R&D 100? And obviously, you have a large team that worked with you on that as well.
Yeah, when we applied for R&D 100, we were in the main question was, is it scalable? Is this system scalable? Because everything changes when you go from the lab scale to the large scale. It changes dramatically because you have to, usually in the permanent magnets, you have to control oxygen, you have to control many things. And when you scale it up, basically it's very difficult to have the same results. But because of the castability of this material, our scaled material was basically the same performance. It had the same performance, and this was very big milestone. Scalability was proven, so we have proven the feasibility of such process. But right now we are already moving forward to really optimize the process and to show that not only it can be done, but it can work in the practical application.
Like we still only have that one question that you already answered. I do again want to thank you for a great presentation. I also think obviously when we look at the difference between the cost and process for neodymium magnets, of course, the strongest magnets in the world, but you being able to get into that middle marketplace with cerium is such a big breakthrough. And obviously we're going to need magnets again with the electrification and of our world. We're certainly going to need more and more magnets in the future. So this can really help in that niche area. I would like to, at this point, again, thank all of our attendees here and want to let you know that, again, this is a webinar series. So we are only in one of the many webinars are going to be presented this year. We're so excited again. And thank you so much, Andriy, for a great presentation again on another R&D 100 award that could inspire several of our researchers out there on this call. The recording is going to be available next week at ameslab.gov/CMI and on YouTube on the Critical Materials Innovation Hub channel. Again, this is monthly. Please join us again for our next webinar on April 30th. Dr. Jun Kui from Ames National Lab is going to present on hot roll nanocrystalline anisotropic neomagnets. It's going to be advertised in the Critical Times. And you can also find it in social media. We are always looking for webinar topics to, again, give you the information that you need as a CMI member and that you would like to see. So don't hesitate to share on the exit survey or email us with a topic that you'd like in the future. So I'm checking to see if we have any additional questions out there. Yes, we've got another question here. Andriy, if you'd like to take that one.
Yeah, sure. This is the question from Shun Being Wrong. If I'm apologizing if I'm pronouncing this wrongly. XRD patterns does not show alignment. Could you please explain again how the good square BH is obtained? You're absolutely right. XRD patterns do not show the alignment. XRD patterns were used to see the secondary phases, to see the precipitations, and XRD patterns didn't show any precipitations. So basically, we were puzzled at the beginning why do we have extrinsic parameters if our phase is not decomposed or if we don't have additional phases. So that's why XRD is not an indicator. So me showing the XRD is actually showing that we don't see something very significant to know what is happening. But squareness, in fact, is because stacking folds are developing, anisotropically and sharing the basal plane with the matrix. That's why we have these square hysteresis loops. But squareness is not related to the XRD. Oh, I would say not directly. Actually, the XRD, which is very, very single phasey, is a good indicator of possible squareness. So it's kind of counterintuitive, I would say. I hope I answered your question.
You got to thank you out there. You did answer the question, so that's great. Well, we do have time for another question. If anybody out there has a burning question or Andriy, maybe you or any of your team members might have any parting thoughts or.
I just wanted to thank everybody, especially to organizers of this great webinar. And thank for getting me a chance to talk about our technology and to basically promote it. Thank you very much.
And thank you. It was an honor to have you on again. For our audience out there, we appreciate your attendance and don't hesitate to join us again on April 30th. Thank you so much, everybody.
Bye.